Hey, welcome back to Fat Mama Physics. Another example on binding energy and mass defect. In this example, we're going to look at, examine the binding energy per nucleon of the nucleus of carbon-12. So we're looking at the nucleus, we're not looking at the atom, which means we have to be very careful about the electrons. We know that carbon-12 has an atomic mass unit of 12U. But keep in mind, this 12U also includes the electrons, which means we actually have to subtract the electrons from carbon-12, from this number, in order just to get the nucleus. We know there's a total of 12 electrons in a carbon-12 nucleus. Atom. So we're going to take 12U and we're going to minus 6 electrons. And if we take a look up here, an electron is essentially 0.00549. And we have 6 of them. So we're going to have to multiply this by 6. Okay? Alright. So, and that's going to give us some number of U. Okay? Oh, shoot. 549. Okay, so 11.996706 U, atomic mass units. Okay, and we want to, first of all, figure out this number. But we also need to figure out, so we want essentially the binding energy, but we also want to find the binding energy per nucleon. But let's do this first. Find out the binding energy, in which to find the binding energy, we need to figure out the mass defect, meaning we need to compare the mass of a nucleus of carbon-12 to the mass of all of the components of a carbon-12 nucleus, which includes 6 protons and 6 neutrons. So if we do that, so 6 protons, every proton is going to be 1.007276 atomic units. Okay, and then for a neutron, this is also going to be 1 point something. What is it? 1.008665. Okay, so then after we add all those atomic units, we get 12.095646 atomic units. And you're right, I could have just worked with kilograms, but I'm just going to multiply by the atomic mass unit kilogram value later in the end. Okay, so let's do a subtraction, which is 12.095646 U minus 11.99676 units. This is equal to 0.09894 units. So to figure out the binding energy, we need to multiply this by the mass of one atomic unit, and later on convert that to amount of energy. So we're going to do that next. And you know what? I'm just going to do it in one go. E equals mc squared, in which my mass is going to be 0.09874 atomic mass units. So times the mass of one atomic mass unit is 1.661 times 10 to the power of negative 27 kilograms. And we're going to multiply by the speed of light, which is 3 times 10 to the power of 8 meters per second, and all of that squared. All of this is going to give us 1.479 times 10 to the power of negative 11 joules. Okay, so to find the binding energy per nucleon, we have the binding energy. Binding energy per nucleon means how much energy is required to hold, say, one nucleon inside the carbon-12 atom. Or nucleus. So essentially for carbon-12, we just need to divide this by the number of nucleons in carbon-12 to figure out how much energy per nucleon in carbon-12. So this is going to be equal to whatever this is divided by 12, which is going to be equal to 1.23. I'll do three significant figures, times 10 to the power of negative 12 joules per nucleon. So the more stable the nucleus, the greater the binding energy there is per nucleon. The interesting thing is you can have two nucleus with a high binding energy, but one nucleus might have more nucleons than the other one. So in fact, it's having a stable nucleus not only means you have a high binding energy, but it also means that you have a high binding energy per nucleon. So either you have a very high binding energy, or you have some binding energy, but you don't have a lot of nucleons you need to hold together, kind of thing. So it's like, you say, let's say you have a family income of a certain amount. If you have more members of the family, then each family member will have less to spend. But if you have a tight, small family, every family member is going to have a greater amount to spend, equivalent to a higher binding energy per nucleon. Okay? Not saying that money holds the family together, but, you kind of get the idea. Okay? So that's it for this show, for this part, which is showing the binding energy per nucleon. So be careful what your nucleus is before you divide by the number of nucleons. Otherwise, there you go. Mass defect to binding energy. Thank you for watching. I wish you good luck. Fat Mama Physics, signing out.